This short video demonstrates how to set up and run a Watbal model to design or evaluate a Piggery effluent system. Watbal is a daily water balance model developed by the Department of Agriculture and Fisheries in Queensland and DHM Environmental Software Engineering with funding support from Australian Pork Limited. Watbal includes provisions for modelling additions to the effluent stream from piggery manure, waste feed, fresh and recycled flushing and hosing water used for shed washdown, any runoff from shed roofs or outdoor production areas, drinking water wastage, and rainfall falling onto pond surfaces. Effluent system extractions incorporated into the model include evaporation from pond surfaces and use of recycled effluent for shed cleaning and application or irrigation onto land growing crop and or pasture. A daily water balance for the soil in the effluent application area is used to trigger effluent application to the land when soil water deficit reaches a selected value. The user can select an appropriate crop or pasture species and soil type for the effluent irrigation area. Data for a range of typical crops, pastures and soils are included in the model. The model uses historical daily climate data which is conveniently downloaded from the Silo Climate Data website. An interactive map is provided to assist the user in selecting the most representative climate data recording station located near the Piggery site. The model accommodates analysis periods commencing from 1900 up until the day prior to the analysis. Other features of the model include the ability to model two effluent ponds operating in series, such as a primary anaerobic treatment pond plus an effluent storage pond, or you can model a single effluent treatment and storage pond. Several common effluent pre-treatment or solid separation options exist, and also a range of primary anaerobic pond design options including conventional large ponds, heavily loaded anaerobic ponds and covered anaerobic ponds. We also have provision for shandying or diluting the effluent by mixing with clean water prior to application to the land. And we have various effluent irrigation management options including variable soil moisture trigger levels and maximum daily application volumes. Watbal produces a range of graphical and textural outputs. The key outputs are presented on the analysis dashboard and include a graphical representation of ponds with key dimensions and volumes, monthly pond storage levels including an 80 percentile band, a 33 percentile band and the mean, a table of storage or single pond water balance components, monthly irrigation amounts, again showing a 90 percentile band and a 33 percentile band and the mean, interactive daily time series charts which include storage single pond levels, overflow amounts, soil water, rainfall and irrigation amounts. The time series graphical outputs have a convenient zoom function which allows users to closely examine the pond performance over a particular period of interest. In addition, the majority of outputs presented in previous Watbal spreadsheet models are accessible via a collapsible according list at the bottom of the dashboard. Setting up a new analysis and entering the data required for a new run for a typical 1000 sow farrow to finish piggery with two pond effluent system located near Dalby in Queensland. Once you've logged into the website, you can go to the analysis menu and select the Create New option. This will create a new analysis using the values of the last analysis you have set up, essentially making a copy of it. If this is your first ever analysis, values will still be pre-populated from a default scenario we have included in the software. First, we're going to enter the details in the analysis setup page. We enter a name to describe the analysis, and then a name for the farm or piggery. Watbal may be used to model either a two-pond or a single-pond effluent system. In a two-pond effluent system, the treatment and sludge storage capacities are provided in a primary pond which overflows into a secondary pond where the effluent storage capacity is provided. Recycled effluent used for shed flushing and recharge and for irrigation into crop or pasture is generally extracted from the secondary storage pond. In a single pond effluent system, the sludge storage, treatment capacity and effluent storage components are provided in a single pond. In our example, we're going to select the two-pond effluent system. Next, we need to select a location, so we can use the tools provided to search for Dalby Post Office, and this pulls down the latest climate data from the Long Paddock website. We then need to select a soil type. We're going to select deep clay loam. We select this from the drop down list and pick the most accurate description for the soil in the effluent irrigation area. The plant available water capacities are provided for each soil type. We then select a crop type. From the drop down list, select a crop or pasture production for the effluent irrigation area. The chart to the right will show the green cover and residue cover over the 12-month growing cycle for the selected crop or pasture. Then we can select a years range. From the drop down list, pick one of the options. Longer periods from 1900 to present will take longer to simulate. So if you're finding analyses are running too slow, pick a later option, say from 1970 onwards. You also can enter in any notes or comments related to this analysis in this text box. Next, we select the Pond Catchment tab. In this tab, we enter any outdoor catchment areas which contribute runoff into the Piggery effluent system. While it's generally good practice to divert runoff away from Piggery effluent systems, in some cases it may be impractical to do so. In cases where piggeries have some outdoor production areas, for example outdoor dry sow accommodation, it's generally considered good practice to collect and treat the potentially contaminated runoff from these areas in the effluent system. The types of outdoor catchments incorporated into the model are concrete, earth, hard, grass, or any vegetated area, and roof. So for each of these components, enter in the appropriate land area sizes. The next three tabs describe the cleaning system used in the sheds where the pigs are accommodated. Tab 3, representing the flushing system, is used to describe the flushing sheds. In these sheds, the pig manure, waste feed and waste drinking water falls or is hosed through the slatted shed floor into the underlying flushing channels. These channels are flushed at regular intervals using clean water or recycled effluent to remove the waste products from the shed into a sump or directly into an effluent pond. In this example, we are assuming that the breeder pigs are accommodated in flushing sheds which are flushed using clean bore water, while the grower finisher pigs are accommodated in pull plug sheds which are recharged using recycled effluent. Some hosing is carried out in all sheds using clean water. The following data is entered to describe the operation of all flushing sheds within the piggery. First, we enter the pig numbers, or the number of standard pig units accommodated in the flushing sheds. Then we enter the flushing interval, so that's days between flushes in the sheds. Then the amount of water used for flushing. Then we enter the total volume of recycled effluent used for flushing all piggery sheds. Next, we enter the average interval between hosings carried out in the flushing sheds. And finally, we enter the volume of fresh water used for each hosing. Tab 4 is used to describe the pull plug sheds housing the weaner, grower and finisher pigs. Pull plug sheds are generally constructed with individual pits under the various rooms within the shed. These pits collect and temporarily store all of the manure, waste feed and waste drinking water which falls or is hosed through the slatted shed floor. The stored effluent is released by gravity from the pull plug pits at regular intervals, typically ranging from 1 to 4 weeks. Following the release of the effluent, the pits are generally partially recharged with clean water or recycled effluent to minimise the tendency for fresh manure to stick to the dry concrete pit floor. The following data may be entered to describe any pull plug sheds within the piggery. First, we'll enter the pig numbers, so this is the standard pig units accommodated in all of the pull plug sheds. Next, we define the release interval. So this is the average number of days between effluent releases from the pull plug sheds. Then we enter the freshwater volume used to partially recharge the pits under the pull plug sheds following the release of effluent from these sheds. Next, we enter the total volume of recycled effluent used to partially recharge the pits under the pull plug sheds following the release of effluent from these sheds. Then enter the average interval between hosings carried out in all the pull plug sheds, and finally enter the volume of fresh water used for each hosing. Tab 5 is used to describe any static pit sheds operating at the piggery. Static pit sheds were commonly used at older piggeries. These pits are constructed under each shed to collect and temporarily store all of the manure, waste feed and waste drinking water which falls or is hosed through the slatted shed floor. The stored effluent is generally released at regular intervals through sluice gates fitted on the ends of the static pit sheds. The effluent released interval is typically up to several weeks. Similarly to pull plug sheds, following the release of the effluent, the pits are often partially recharged with clean water or recycled effluent to minimise the tendency for fresh manure to stick to the dry concrete pit floor. In this example, there are no static pit sheds within the piggery. However, if we were going to set this up, we would enter the number of standard pig units, then the release interval between effluent releases from the static pit sheds. We'd enter the volume of fresh water used to partially recharge the pits under the static pit sheds following the release of effluent from these sheds. Then we'd enter the total volume of recycled effluent used to partially recharge the pits under the static pit sheds. Enter the average interval between hosings carried out in these sheds, and finally enter the volume of fresh water used for each hosing. Tab 6 represents the solids management of the piggery. This is used to enter the estimated total solids or TS and volatile solids VS loadings into the effluent stream discharged from the piggery shed. A drop-down list is provided to select any solids separation method used to remove solids from the effluent after it leaves the sheds and prior to entering the effluent pond system. If no solids separation systems are used, select None. If an alternative type of solid separation is to be used, select Other and enter the expected total solids and volatile solids removal rates for the alternative system. In the current example, we're assuming that a static rundown screen is being used. So to enter the values into this section, firstly we enter the total solids or TS from the sheds, and then the volatile solids VS from the sheds. Solid separation, we've selected static rundown screen. So from the drop down list, select the method that will remove the solids from the shed prior to discharge into the pond. If no solid separation system is used, select None. If an alternate type of use, select Other and enter the expected TS and VS amounts. Tabs 7 are to represent our primary and storage ponds. So tab 7A is used to enter data relating to the primary anaerobic pond, used to treat the effluent discharged from the sheds or following pre-treatment in a solids separation system. Watbal automatically calculates the anaerobic pond activity ratio K for the piggery site based on the temperature data in the imported silo climate data file. Once the pond design philosophy is selected, the Watbal model determines the recommended maximum VS loading rate from the baseline VS loading rate and K value. The second criterion used by Watbal for determining the minimum active treatment volume is the hydraulic retention time, which should generally exceed 30 days, based on the estimated primary pond inflow rate. Once the pond desludging interval is selected, the recommended minimum sludge storage volume is calculated based on the standard sludge accumulation rate. These two volumes are then added together to give the minimum recommended pond volume shown in the primary pond active volume graphic below the data entry tab. The total pond volume entered in the data entry tab should generally be greater than the minimum recommended volume. The various key pond dimensions can then be entered, and Watbal automatically determines the other dimensions and displays them on the primary pond graphic. So first we select our pond design philosophy. So from this list, pick the approach that we're going to use to design the primary anaerobic effluent pond. So we can choose a conventional large, a heavy loaded anaerobic pond, or a covered anaerobic pond. In this case, we're going to pick conventional large. Refer to section 10.3 NEGP from Tucker 2018, the third edition, for further details. The selected design approach will dictate the suggested volatile solids loading rate and ultimately the required active treatment volume. Next we pick our desludging interval, which we enter as 2 years, enter the proposed time between the pond desludging events. So it's generally half a year up to 10 years. The total pond volume to be entered in meters cubed. So for effective anaerobic treatment, this volume should generally be equal to or greater than the minimum recommended volume provided in the graphic below. Then we enter the pond storage depth to establish and maintain conditions that promote anaerobic decomposition of the organic matter in the effluent stream. A minimum pond depth of 2.5 metres is recommended. For ponds with capacities greater than about 1 megalitre, depths of 5 metres are common. The depth to any underlying groundwater and rock should also be considered in selecting the pond depth. Then we need to enter the batters, the lengthwise and breadthwise batters. So pond batters are the slopes on the side of the pond. Batter slopes are expressed as the number of horizontal units for a rise of 1 unit vertically. So they should generally be as steep as possible, provided the sides of the pond remain stable. Consequently, the batter gradient may change for different soil types, but should generally be no steeper than 1 vertical is to 2 horizontal, which is about 26.6 degrees or 50%. Flatter batters maintain better embankment stability, facilitate compaction, protect against wave erosion, and improve safety in pond construction and maintenance. Next, we need to enter the length at the embankment crest. So you enter the preferred length of the longer side of the rectangular primary effluent pond at the crest of the embankment. So in choosing this dimension, consider any site constraints which may limit the pond dimensions. Next, we enter freeboard. So the freeboard from the full storage level or overflow level to the crest of the pond embankment should be at least 0.6 of a metre to account for wave action, bank settlement and increased water levels during overflow events. Finally, we enter the cover anchorage allowance. So for covered anaerobic ponds, enter the additional cover length from the top of the embankment crest to allow for trenching the cover into the pond embankment. So generally approximately 3 metres. Tab 7b is used to set up the data for the storage pond, which receives all of the effluent overflowing from the primary anaerobic pond. So recycled effluent used for flushing or recharging pits under the piggery sheds and irrigation onto crop or pasture is drawn from the storage pond. The size of the storage pond should be sufficient to store excess effluent, not required for shed cleaning during periods of extreme or extended wet weather, when the soil in the effluent irrigation area is too wet for effective effluent application. If the soil water storage profile in the effluent application area is relatively full, further application of effluent onto this area may result in runoff and or leaching and possible export of nutrients and pathogens which may contaminate surface water and or groundwater resources. Regulatory agencies generally specify a minimum spill reoccurrence interval, typically 10 years, to minimise the risk of spilled effluent contaminating the surrounding environment. This design standard may be varied depending on the sensitivity of the receiving environment. Along with several irrigation management factors, the size of the storage pond is one of the main determinants of the spill recurrence interval, which is shown at the bottom of the storage pond active volume graphic below. The iterative process for determining optimal storage pond size generally involves entering an initial pond capacity and dimensions through this storage pond tab. Several effluent irrigation parameters may then be entered on the next tab, the effluent irrigation, before checking to see whether the average spill reoccurrence interval is less than 10 years or some other agreed performance standard. So to enter our values in here, we need to estimate a total storage capacity. This capacity can be adjusted along with relevant parameter values to produce the desired number of spill events over the selected analysis period. The next one is the total storage depth of the secondary pond. So secondary ponds are generally designed for storage of treated effluent rather than the anaerobic treatment. Consequently, they may be shallower than primary anaerobic treatment ponds. The depth to any underlying groundwater or rock should be considered in selecting an appropriate secondary pond depth. Next, we put in the residual storage depth. So no further effluent is removed from the storage pond for either irrigation or shed flushing purposes once the storage volume is deleted below this level. So this depth can be used to represent the storage depth that cannot be practically pumped out. So generally pumps require at least half a metre of submergence over the suction to operate satisfactorily. Next, we need to enter the length at the embankment crest. So this is the longer side of the rectangular secondary effluent pond. In choosing this dimension, consider any site constraints which may limit the pond dimensions. Next, we enter the batters, both lengthwise and breadthwise. So as we mentioned with the anaerobic pond or the primary pond, pond batters are the slopes of the sides of the pond which are generally expressed as a number of horizontal units for a rise of 1 unit vertically. This will depend on soil type, and typically no steeper than 1:2, which is about 26.6 degrees or 50%. And the flatter batters are better to maintain embankment stability, facilitate compaction, protect against wave erosion, etc. Finally, we need to enter the freeboard. So this is from the full storage level or the overflow level to the crest of the embankment pond, and it should be at least 0.6 of a metre to account for wave action and bank settlement, etc. Finally, we have our last tab, which is used to enter data relating to the effluent irrigation system, which is used to apply recycled effluent from the storage pond onto an area of land growing a crop or pasture. The crop or pasture growing in the effluent irrigation area and the soil type in this area were both previously entered on step 1, the first tab, in analysis setup. Along with the storage pond size, the parameters entered in this tab may have a major influence on the storage pond spill reoccurrence interval. So the first thing that we need to do is select an irrigation method. So from the drop-down list, choose the method that applies to your method of irrigation. Then we need to define our irrigation area. This is the land over which the effluent from the pond system will be applied. This area may be limited by practical, economic, social considerations such as the availability of irrigated land, the cost of equipping the area with irrigation infrastructure, and proximity to neighbouring dwellings. We then enter a pump capacity, which is in megalitres per day. So this limits the amount of water we can put on per day. It's the nominal operating flow rate of the effluent irrigation pump. This sets the maximum volume of effluent which can be irrigated in a day. It's assumed that the minimum daily volume is a quarter of this value. The assumption reflects the impracticality of operating an effluent irrigation pump for less than 6 hours per day. Then we need to enter a rainfall amount that, should we receive that amount, we don't irrigate. So this is the minimum daily rainfall required to cancel our irrigation practice. So in the simulation, Watbal won't allow effluent irrigation on days when rainfall totals equal to or greater than this amount. The last option is our shandying amount or effluent dilution. So this is the percentage of effluent in the diluted mixture applied to land growing crop or pasture in the effluent irrigation area. So for example, if underloaded effluent is applied, enter 100%. If the effluent is mixed with an equal volume of clean water, enter 50%. If 1 part of effluent is mixed with 4 parts of clean water, enter 20%. Lastly, on our right hand side, we have the monthly deficits for irrigation to occur. So for each month we enter the soil moisture deficit below wilting point or drained upper limit, used to trigger the commencement of effluent irrigation. So the model does not allow effluent irrigation to commence when soil moisture is greater than this value, so no irrigations will be triggered. Lower values generally result in higher pond spill reoccurrence intervals due to smaller, more frequent effluent applications. However, higher levels of management and labour input are generally required. Note that you can turn off irrigation in certain months by setting the deficit amount to none.